I'm gonna start this video by looking at a number theoretical function, the Euler function. And the reason for that is because the theorem we're gonna cover in this video lecture talks about this function there. Now, let's look at the definition. So the function, the Euler function, it takes as an input natural numbers, and the output is also natural number. It is defined like this. What is phi of any natural number is the number of positive integers less than or equal to n that are relatively prime to n. Now, relatively prime means that the greatest common divisor between that number and n will be 1. Now, if you want to be precise about the definition, that would be this here, number of elements. That's what the bars here mean. Number of elements of this set. And this set is the collection of the natural numbers k and n. Those natural numbers are positive, of course, less than or equal to n, and the greatest common divisor between n and k is 1. That's what it means to be relatively prime. The greatest common divisor is 1. So let's do some examples with computation using the definition. Now, what would be phi of 1? Now, if you look at the definition, that would be the numbers, natural numbers less than or equal to 1 that are relatively prime to 1. The numbers that are less than or equal to 1 that are natural numbers, there's only one, it's just the 1 itself. So that is just 1. That's relatively, 1 is relatively prime to 1. Now let's do that with 10. So phi of 10. So this is phi. So you read like the function phi, Greek letter. Now we look at the positive integers less than or equal to 10. We are using the definition. So that's just this collection right here. And from that collection, we're going to choose the ones that are relatively prime to 10. So from here, choose the ones that have common divisors with 10, only 1. So that would be 1, 3, 7, and 9. Now the answer for phi of 10 should be the number of elements that are here. So we have 1, 2, 3, 4. So there's 4 of them. So phi of n is counting. It's a counting function. So it's counting how many elements, how many natural less than or equal to 10 are relatively prime to 10. Now, as you can see here, if you increase the number here, it will be a little bit tedious to use this definition. So there are some properties that's going to help us do computations a little bit faster for some particular cases. So these are some properties we can use. So if you have a prime number, you can compute easily phi of that prime number. That's just the prime number minus 1. So it's p minus 1. Of course, you have to know that this p is a prime number. There's also another property. If you have a power of a prime number, then you can compute phi of that relatively easy. So p is a prime number here. K is a natural number, any natural number. So phi of p to the k power is p to the k, and then you subtract 1 power less than p to the k. So p to the k minus p to the k minus 1. And this quantity here is the number of naturals less than or equal to p to the k that are relatively prime to p to the k. Now this is also very useful, this other property number 3, and is this. If you have two natural numbers that they are relatively prime, so that the greatest common divisor between them is only 1, so they have no common factors other than 1, then you have this property for phi of n. So phi of the product n times n, you can distribute the phi to the m and to the n. So it's phi of m times phi of n. Now this is a very useful property, and we're going to see how we use it in a second. I'm going to give you some examples. Now, you have to be careful when you apply this property. This only works if m and n are relatively prime. It doesn't work in any other cases. Okay, so let's see some examples. Let's say you have the number 11 here. Now, phi of 11. Now, we know 11 is a prime number, so it's just p minus 1. So just 10. Now, always read down what this means. So 10 is the number of naturals less than or equal to 11 that are relatively prime to 11. So there's 10 of them. Let's do the same. So here for this one, phi of 3 to the 4. So we're going to apply some of the properties. Now, 3 here is a prime number. So I can apply this property here, this one. So you have a prime number to a power, to a natural number power. Then we apply this property. So this is going to be 3 to the 4, so the same thing here, minus 3 to the exponent, which is 1 less than this one. So that's the property. So then 3 to the 4 is 81, 3 cubed is 27, and then you do the subtraction, and that gives you 54. Now, also remember always, what is 54? 54 is the number of naturals less than 3 to the 4 that are relatively prime to 3 to the 4. You see, this is much better to compute this way than using the definition, because if you want to use the definition for this one, 3 to the 4 is 81, so you will have to list 81, all the elements from 1 to 81, and then check which ones are relatively prime. So that's going to take longer than just doing this computation here. So that's the advantage of using the properties. Now, how about a number that is not a prime of a power of a prime? So for example, a number like this one, 320. For this type of number, the next best approach will be to factor the number into prime numbers. So we first find the prime decomposition of factorization of 320. So how do you do that? So there are several ways in which you can find the prime decomposition of 320. One way to do it is this way. You can do it any way you like. Is this. I'm going to put a number 320 here, a vertical line, and on this column, I'm going to put the primes that divide 320 in order. Now, it's a good idea to have a list of prime numbers before you start doing this. For example, 2, 3, 5, 7, and 11. That's probably enough for this number. Okay, so you're going to start like this. So check which prime number divides 320 from your list, from this list. So 2 divides 320. 320 is even, so 2 goes even into 320. So we're going to do the division. So 2 into 320, that's 160. 160. Now, if 2 is again into 160, then we do it again. So 160 is divisible by 2, so I'm going to put another 2 there. And I'm going to take half of 160, and that, of course, is 80. If 2 is also evenly into 80, you do it again. So 2 goes into 80. That's 40 times. We do it again. 2 goes into 40 20 times. And 2 goes into 20 10 times. You can do it one more time. 2 goes into 10 5 times. And that's it. 2 doesn't go into 5 evenly, but so then we look at the next number on the list, 3. So 3 doesn't divide 5, and then we go to the next one, 5 divides 5, so we're gonna put down that one. So 5 divides 5, and it gives 1. So we stop there because there is no prime number that divides 1. So that will this column here will give us the prime decomposition of 320, and that's going to help us find phi of that. So let's write down the prime decomposition. It's going to be 320, and it's going to be number of powers that you have, of primes that you have here of 2. So you have 1, 2, 3, 4, 5, 6. So that's 2 to the 6th power times the other prime number, which is 5. This one right here. Now this prime decomposition is going to help us find phi of that number. So phi of 320 is going to be phi of 2 to the 6 times phi of 5. And now why am I doing that? Why am I putting the 5 here and here? Because these two numbers, 2 to the 6 and 5, are relatively prime. And by the property, the third property we saw for this function, when you apply the function phi to this, it distributes. So it's phi of the 2 to the 6, phi to the 5. Now we can use some of the properties, other properties, to keep simplifying this. So we apply a property to this one. Now if you look at that, that is a power of a prime number. That's 2 to the 6. Now by the property that we saw already, that's going to be 2 to the 6 minus 2 to 1 power less 2 to the 5th. Now for this other one, for number 5, is here for the number 5, phi applied to 5. 5 here is a prime number, so we can use the property for prime number. So that's going to give us the prime number minus 1. And then the only thing you have to do here is just simplify the computations. So you simplify here, that's gonna 2 to the 6 is 64 minus 2 to the 5th is 32. That multiplies 5 minus 1, which is 4. So that's gonna give us 32 here. That's because it's 64 minus 32 times, and then times 4. Times 4. And that's gonna give you 128. Now, whenever you do the computation, always remember what it means. So what is the meaning here of this number 128? So 128, remember this function is a counting function. So it's counting the number of naturals that are less than or equal to 320 that are relatively prime to 320. So that's what this 128 means here. So this is kind of like sort of overview of the function, the Euler function. And the reason for that is because of the next theorem that actually talks about this function. So this is the main purpose of this lecture. So this theorem here. So let's look at the theorem and what it says. So the theorem has a title and is number of elements of order D in a cyclic group. So let's see what this statement says. So we have a group and it's cyclic, so that's important. A group of cyclic that is order n, so it's a finite cyclic group. It has some order n. If you have a divisor D, if D divides n, then the number of elements in G of that order D is phi of D. So this theorem is telling us the number of elements in G that have a particular order. Now, so it's gonna be that's phi of D, that's the Euler function, that's the one that we review at the beginning of this lecture. So that's why I had to review that. Now, I'm gonna prove this theorem, and the reason to prove this theorem is because it has a nice idea. So sometimes I prove theorems, sometimes I don't. One of the reasons to prove it is it has a nice idea and it is not too long. And one of the reasons I don't prove theorems is because maybe the proof is very tedious and long and doesn't have that nice of an idea of the proof. Those are the reasons. All right, so let's look at the proof here. So I have to prove that if the number of elements of order D in the group G is this one. So it's a counting theorem. So let's look at that. So it's an if-then. So we're gonna assume that we have a group that is cyclic, that the order of that group is n, and that D is a natural number that divides n, and here is the number of elements in that group. Now, G is cyclic. That's the assumption that we are making. That's the theorem. You have to have G cyclic group. We're gonna use the fundamental theorem of finite cyclic groups, the one that we covered in previous lecture. So by that theorem, remember that theorem has 3 parts. If you don't remember that, go and review that theorem, fundamental theorem of finite cyclic groups. One of the things that the theorem said was that G has a unique subgroup of order D, because D divides n. For any divisor of the order of the group, there is a unique subgroup of that order. The important word here is unique, so there's only one of them. So there is a unique subgroup of order D. Now we're gonna call that subgroup H. So H is the only subgroup of G that has order D. So that's, now we also know that that subgroup is cyclic. That's also by the fundamental theorem, because any subgroup of a cyclic group is also cyclic. Now if you don't remember this, you have to go back and check that video lecture. All right, so let's go with the proof. So I have to count the number of elements of order D. Now, the number of elements of order D in G is going to be finite because G is finite. So I'm going to have a finite number of them. So let's call the elements of order D, let's label them as A1 through AR. So these are all the elements of order D in G. There's a finite number of them because G is finite. Now, what do we have to prove? We have to prove that this number here is phi of n. How many are here? 1, 2, up to r. So we will have to prove that r is equal to phi of d, or the number of elements. So this number of elements here is phi of d. That will be the goal of this. Now, one of the things that we're going to prove within this theorem is that these elements that are all the elements of order d, all of them are going to be actually the generators of this H, the subgroup, the only subgroup of order D. So the only subgroup of order D has as generators all the elements of order D. That is an assumption that that's not an assumption, that's something that we're gonna prove here. And that's the next claim. So the next claim is this: all the generators of H, all of them, are that precisely the elements A1, A2 through AR. So that means all the generators of H are exactly the elements in G of order D. So that would be our claim. So we're going to prove the claim. So let's look at that. So what do I have to prove here? So they have to prove actually a couple of things. One is this: if I have a generator of H, I need to show that that generator is one of this. And I also have to prove that these elements here are also generators of H. Those couple of things will prove that all the generators for H are this one. This is sort of like an if and only if. You have a generator of H, it has to be this, one of this. And if you have one of this, that is a generator for H. Now let's prove the claim here. So let's take an arbitrary element here from this list, from the elements of order D. So if you have an element of order D, so A sub I, just a generic one from here, has order D, the subgroup that this element generates, which is, remember, the subgroup generated by that element, all powers of A sub I, has also order D, has the element. We have proved that already. If you have an element of order D, the subgroup generated by that element has order D. By the fundamental theorem, there is only one subgroup of order D, and we know which one is that, is H. So by the fundamental theorem, there is only one subgroup of order D, and that was H, so H has to be this one. Now this here, it means that an arbitrary element from this list is a generator of H. So that's what I say here. That is, AI is a generator of H. That's not the end. I also need to prove that if I have a generator of H, then it has to be one of this. Okay, so let's take a generator of H here. So what that means is that all the powers of A will give me the whole subgroup H. Now, I know that H has order D. That's exactly what we are saying. H has order D. It's the only subgroup of H that has order of G has order D. So we must have that the order of A has to be D, because the order of the subgroup has to be the same as the order of the generator. So the order of A has to be D. If the order of A is D, and this list right here are all the elements of order D, then A has to be one of them. So that is, A must be one of these elements. That all proves that A1 through AR are exactly all the generators of H. So let's emphasize that idea here. So the conclusion here will be that H is generated by all of those elements, and this one are all, that's the important part, are all the generators of H. Now remember what this list initially is. This list is all the elements of order D. So we just have proof that all the elements of order D are exactly all the generators of the group, the subgroup H. All right. Now, so I have here the list of elements of order D. So let's look at the first element here in this list, A1. Now, I know that H is generated by A1. Why? Because it's generated by each one of them. We have proved this corollary. If you have a generator of a group, and a generator of that group is a power of this, of the generator to the k, where that exponent is between 0 and D. D is the number of elements in that group, subgroup, and the GCD between k and d is equal to 1. This is one of the corollaries we proved about the generators, and we did a couple of examples with this. So if I have generator A1, any other generator will have the form A1 to the k, where k is between 0, less than or equal to d, and the GCD between k and d is 1. So what does that mean? It means that the number of generators of H, because these are all of them, that will correspond to the number of ways in which I can choose my k here, because each one of these choices of k will give me a generator for H. So I can write down this like this. So what is the number of generators here of this one? Is the exponents that are between 0 and d. So the GCD between k and d is equal to 1. That's because of the corollary we proved about the generators of a cyclic group. But if you look at this here, this one right here, that is exactly the definition of the function phi. Phi is the number of elements between 0 and d that are relatively primed to d. And so that by definition is phi of d. So I'm going to call this one number 1. I hope that was clear. Now I'm going to look at it in another way. Now we also know that the number of generators of H is this one, because that's what we prove in the claim. The number of generators here is the number of elements in this set, which is R. That's by the claim. Now if you compare 1 and 2, what we are saying is that R is equal to phi of d. That's exactly what we wanted to prove, but let me emphasize that a little bit more. What that means is, what is R here? R is the number of elements in G of order D. The number of elements of order D in G is phi of d. So that is exactly what the proof is. Alright, the reason I did this proof is because it has a nice idea about counting. So that proves the theorem. Okay, let's look at some examples using that theorem. So the theorem can only be applied if you have a cyclic group. That's very important. So let's look at this example. So Z12 with addition. Now this is a cyclic group. That is, remember, the elements of Z12 are 0, 1 through 11. And this group is cyclic. Why? Let me just write down why is that. Because Z12 is generated, for example, by the number 1. So that is a cyclic group. So the addition here is addition modulo 12. And so we can count the elements of orders in Z12. For example, we know that 4 divides 12. So because 4 divides 12, this is the D and this is the N. So we can ask the question, how many elements of order 4 this group have? Now 5 doesn't divide 12. So 5 here, there are no elements of order 5 in Z12. But for any divisor, there will be elements of that order. So we know that 4 divides 12, so we know that this group has elements of order 4. Now if 5 doesn't divide 12, then in example, for example, 5 doesn't divide 12, then this group doesn't have elements of order 5. So because 4 divides 12, we can find the number of those elements there. So Z12, we had phi of 4 elements of order 4. So we compute this to see how many elements of order 4 will this group have. So phi of 4 will be phi to 2 squared, and remember, by the property, you have a prime number to an exponent is 2 squared minus 2 to the first power by the property we saw earlier. So that's going to be 4 minus 2, that's 2. What does that mean? That this group Z12, let's look at the conclusion here. Z12 has 2 elements of order 4. You can ask the same question for all the divisors of the order of this cyclic group Z12. Remember, this theorem only applies for cyclic groups. So let's look at here at all the possibilities. So the divisors of 12 are 1, 2, 3, 4, 6, and 12. That's all the divisors. For every divisor, I can ask the question, how many elements in Z12 will have this order? So by the theorem, the Euler function applied to 1, so it's 1. The number of elements of order 2 in Z12 is phi of 2, which is also 1. And you do the computation for each one of them. So the computations are all here. So you just have to find phi of that function. Let's say, for example, for order 6. So for order 6, the number of elements of order 6 in Z12 will be phi applied to 6. And we can compute phi of 6 like this. We can split it up as phi of 3 and phi of 2. Because 6 is 3 times 2 and 3 and 2 are relatively prime. Phi of 3 we know already that is 2 from here. And phi of 2 is 1, so that gives me 2. One thing that I want to point out here is the last one. The elements of order 12 in Z12 will be actually the number of generators in Z12. So, because a generator will have order 12 of Z12. So, the number of the generators of Z12 will be phi of 12, and we can compute that by making a decomposition of 12 as 4 times 3. So it's phi of 4, phi of 3. Now phi of 4 is 2. The phi of 3 is also 2, so it's going to be 2 times 2. That's why we get a 4. So then in that case, we can count the number of generators there without having to go through the list of the generators. We know how many they are. So this one has 4 generators. So that's kind of like a nice corollary of that theorem. All right. So that's all I have to say about this theorem so far. In the next video, I'm going to do another example of the theorem, and then we'll continue with the next chapter, which is chapter 5. Okay, that's all. Take care and good luck.